Hello everyone! This week we will cover Module 5 of Chem 1. We will discuss the valence-shell electron repulsion theory. The Lewis bonding theory gives a simple explanation for how covalent compounds form. Although this theory makes it easy to understand covalent bonding, it has its limitations. First of all, it is mainly applicable to elements in period 2 of the periodic table. Second, it has limited application for elements that do not follow the octet rule. Third, it is one-dimensional. It does not show the shape of molecules. To address the limitations of the Lewis bonding theory in terms of geometric structure, British scientists Ronald Gillespie and Ronald Nyholm proposed the VSEPR theory in 1956. The theory's premise is that a molecule will adopt the geometric shape that best minimizes the repulsions of the electron pairs of its central atom. By understanding how electrons repel each other, the VSEPR theory has done a pretty good job of predicting what geometric shape a certain molecule will have. According to the VSEPR theory, electron pairs in the valence shell of an atom tend to orient themselves so that the total energy is minimized. Electrons around the central atom arrange themselves as far apart from each other as possible. The best arrangement is the one with the lowest energy level for the molecule. The geometric shapes predicted using the VSEPR theory falls into 5 basic shapes. The linear shape with a predicted bond angle of 180 degrees, the trigonal planar shape with a predicted bond angle of 120 degrees, the tetrahedral shape with a predicted bond angle of 109.5 degrees, the trigonal bipyramidal shape with predicted bond angles of 90 degrees along the eggshell plane and 120 degrees along the equatorial plane, and the octahedral shape with predicted bond angles of 90 degrees. There are certain features of the VSEPR theory that we must remember. First, it considers only the electron pairs in the valence shell of the central atom. The electron pairs, both lone pairs and bonding pairs, and single unpaired electrons form electron groups. The limitation of the VSEPR theory is that it does not show the number of bonds, whether single, double, or triple, between atoms. How does the VSEPR theory predict geometric shapes? By understanding how the electron pairs in the central atom behave, we can determine what their effect will be to the orientation of the terminal atoms. For instance, in the molecule carbon dioxide, carbon shares all of its valence electrons with the 2 oxygen atoms. This results in a linear orientation. On the other hand, in the water molecule, the 2 electron pairs in oxygen that do not participate in the bonding causes the hydrogen atoms to bend. Before we begin to learn about the different molecular geometries, we must first learn how to count electron groups. Electron groups refer to the bonding pairs and lone pairs around the central atom. Each lone pair of electron is one electron group. Each bonding pair of electron, whether single, double, or triple, is considered one electron group. Let's look at the central atom in the carbon dioxide molecule. Carbon forms 2 bonds with 2 oxygen atoms. Each double bond is counted as one electron group. So, carbon dioxide has 2 electron groups made up of 2 bonding pairs of electrons. How many electron groups does the water molecule have? Let's consider only the electron pairs around the central atom oxygen. Oxygen shares 2 single bonds with 2 hydrogen atoms, so it has 2 bonding pairs. It also has 2 lone pairs of electrons. So, in total, there are 4 electron groups around the oxygen atom. The VSEPR theory enables us to add another layer of description for representing molecules. We can refer to this as their three-dimensional shape or molecular geometry. In the Lewis dot structure, water is represented as one-dimensional. We use the ball and stick model to represent its three-dimensional shape. The balls represent the atoms and the sticks represent the bonds. Another way to represent molecule shape is by using the wedge and dash system. The solid wedge represents an atom oriented toward the viewer, and the dashed wedge represents an atom oriented away from the viewer. In the VSEPR notation, the central atom is designated by the letter A. The terminal outer atoms are designated by the letter X. And any lone pair electrons is designated with the letter E. The general notation is AXMEN, where M refers to the number of terminal atoms and N refers to the number of lone pair electrons. Now let's go over the different molecular shapes predicted using the VSEPR theory. The simplest shape is one with only two electron groups around the central atom, and both of them are bonding pairs. The VSEPR notation is AX2. A linear shape results when the bond angle between the terminal atoms is 180 degrees Celsius. Examples of linear molecules are carbon dioxide and beryllium difluoride. The next basic shape is achieved with three electron groups. All three groups may be bonding pairs, or there may be two bonding pairs and one lone pair. The VSEPR notation is either AX3 for molecules without a lone pair, or AX2E for molecules with two bonding pairs and a lone pair. For the AX3 notation, the resulting geometry is trigonal planar. For the AX2E notation, the geometry is bent. For both shapes, the predicted bond angle is 120 degrees. Examples of trigonal planar molecules are boron trifluoride, sulfur trioxide, and the carbonate ion. Examples of bent molecules are tin-2 chloride, ozone, and sulfur dioxide. A different geometric shape is achieved with four electron groups. The electron groups can be made up of all bonding pairs, three bonding pairs and one lone pair, or two bonding pairs and two lone pairs. The VSEPR notation is AX4 for four bonding pairs, AX3E for two bonding pairs and one lone pair, and AX2E2 for two bonding pairs and two lone pairs. The molecular geometries that result from four electron groups are tetrahedral, trigonal pyramidal, or bent. The predicted bond angle is 109.5 degrees. An example of a tetrahedral molecule is carbon tetrachloride. An example of a trigonal pyramidal molecule is ammonia. And an example of a bent molecule is water. Another set of basic shapes forms with five electron groups. The electron groups can be made up of five bonding pairs with a VSEPR notation of AX5, four bonding pairs and one lone pair represented by AX4E, three bonding pairs and two lone pairs represented by AX3E2, or two bonding pairs and three lone pairs with a VSEPR notation of AX2E3. The molecular geometries that form with five electron groups are trigonal bipyramidal, seesaw, T-shaped, or linear. The bond angles are 120 degrees along the equatorial axis or x-axis and 90 degrees along the eggshell or y-axis. An example of a trigonal bipyramidal shape is phosphorus pentabromide. An example of a seesaw shape is sulfur tetrafluoride. Iodine trichloride is a T-shaped molecule, and the iodide ion is an example of a linear molecule. This linear molecule is different from the one we learned earlier because this one has lone pairs of electrons, whereas the other linear geometry has no lone pairs. Finally, we have molecules with 6 electron groups. The electron groups can be made up of 6 bonding pairs with a VSEPR notation of AX6, 5 bonding pairs and 1 lone pair represented as AX5E, and 4 bonding pairs and 2 lone pairs represented as AX4E2. The molecular geometries that arise from these electron group combinations are octahedral, square pyramidal, or square planar, with bond angles of 90 degrees all around. An example of an octahedral molecule is sulfur hexafluoride. An example of a square pyramidal molecule is iodine pentabromide. And an example of a square planar molecule is xenon tetrafluoride. Let's apply the VSEPR notation to determine the molecular shape of a molecule. Our first step is to draw the most likely Lewis structure of the given molecule or polyatomic ion. We will use the hydronium ion as our example. We can draw the Lewis structure of the hydronium ion based on the structure of the water molecule. Note that this ion has a +1 charge, which means it loses 1 electron. In the water molecule, oxygen shares 2 electrons with hydrogen atoms, and it has 2 lone pairs. In the hydronium ion, there is another hydrogen atom and 1 electron is lost. So if you remove this and pair this to the other hydrogen atom, we can draw the Lewis structure of hydronium ion as oxygen attached to 3 hydrogen atoms and 1 lone pair with a +1 charge. The next step is to determine the VSEPR notation of our molecule. So, let's go back to our hydronium ion drawing. So, looking at this drawing, the oxygen atom has 1 lone pair and 3 bonding pairs. So, its VSEPR notation would be AX3E. Then we can determine the molecular shape using the VSEPR notation. So, AX3E corresponds to 4 electron groups and 1 lone pair. This gives the hydronium ion a trigonal pyramidal shape. We can then draw the perspective drawing of the hydronium ion based on our guide. We put the oxygen atom in the center with its 2 lone pair electrons. Draw one H oriented along the plane of the page, another H oriented towards the viewer, and the other H oriented away from the viewer. We learned in previous modules that particles with like charges repel each other. This is true for electron pairs. Electrons repel each other regardless of whether they are lone pairs or bonding pairs. It is actually this electron repulsion that gives molecules their unique shapes. Electron-pair repulsions are greatest between lone pairs, intermediate between a lone pair and a bonding pair, and weakest between two bonding pairs of electrons. Repulsive forces decrease rapidly with increasing angle between the central atom and the terminal atoms. Thus, repulsions are greatest at 90 degrees, weaker at 120 degrees, and weakest at 180 degrees. Let's go back to one of the molecular shapes discussed earlier. Molecules that have 4 electron groups have 3 possible molecular geometries. We note here that the predicted bond angle for these 3 shapes is 109.5 degrees. However, this is only true for the tetrahedral shape. The other 2 shapes have a slightly different bond angle. This difference is largely due to the presence of the lone pairs of electrons around the central atom. Let's look at how electron-pair repulsions affect molecular geometry. Lone pair electrons tend to occupy more space in a molecule than bonding pairs. In the case of ammonia, the lone pair in nitrogen pushes the bonding pairs with hydrogen away. Let's determine what type of electron-pair interactions there are in this molecule. The ammonia molecule has 3 lone pair bonding pair interactions between the lone pair in nitrogen and the 3 hydrogen atoms. The 3 hydrogen atoms have 3 bonding pair interactions between them. The bond angle is 107 degrees instead of the predicted 109.5 degrees. Another molecule with 4 electron groups is water. It has 1 lone pair interaction between the 2 lone pairs in oxygen, 4 lone pair bonding pair interactions because each lone pair has 2 interactions with the 2 hydrogen atoms, and 1 bonding pair interaction between the 2 hydrogen atoms. The bond angle becomes 104.5 degrees. These new bond angles were determined from laboratory experiments. Going back to the tetrahedral shape, carbon tetrachloride has no lone pair electrons, so the chlorine atoms arrange themselves equally around the carbon atom, resulting in equal bond angles as predicted. We can also determine the molecular geometry of molecules with more than one central atom. We do this by determining the shape around each central atom and orienting the atoms as predicted. Let's use ethanol as our example. It is made up of 2 carbon atoms and 1 oxygen atom with 6 hydrogen atoms attached. Let's start with this carbon atom. It has 4 electron groups made up of 4 bonding pairs. Its VSEPR notation is AX4, which corresponds to a tetrahedral shape. The next carbon atom also has 4 electron groups made up of 4 bonding pairs. So its VSEPR notation is AX4, which corresponds to a tetrahedral shape. Now we go to the oxygen atom. It has 2 lone pairs and 2 bonding pairs, which gives it 4 electron groups. So its VSEPR notation is AX2, E2, which corresponds to a bent shape. We can redraw this Lewis structure to reflect the bent shape of the oxygen portion of the molecule. So first, we draw the central atoms. attach the hydrogen atoms to carbon, and we can draw the H here and then add the lone pair electrons. We can represent the three-dimensional shape of ethanol using the perspective drawing technique or the ball and stick model. And that ends our lecture on the VSEPR theory. The deadline for submission of Module 5 activity worksheet will be posted in Google Classroom. Instructions on how to submit the requirements are written in the module. Thank you for listening.